This is the Discovery Files podcast from the U.S. National Science Foundation. From traffic to blaring TVs and the speakers in portable devices, we are surrounded by noise. Tens of millions of Americans suffer from a range of adverse health outcomes from noise exposure, directly to your ears in hearing loss or psychological effects from long-term exposure. We are joined by Dr. Grace Yang, who, as part of the Fiber Group, worked on her doctorate degree in the Department of Chemical Engineering at MIT, developing materials with acoustic properties, able to be used for sound suppression or noise cancellation applications, or even as a microphone. Dr. Yang, thank you so much for joining us today.
Thank you so much for having me. Happy to be here.
As someone who's interested in chemistry, how did you get to material science and fibers?
During my undergrad, I had the opportunity to do research in a few different research groups. And while the work in each group was pretty different, the common thread was kind of materials. And those positive research experiences really influenced me to pursue my PhD in chemical engineering with the goal of working on research that is materials related. And once I started at MIT and began to look for a research group, I really was gravitating toward projects that have a kind of immediate application and projects that involved a lot of hands-on work. And when I met Professor Yoel Finks, who ended up becoming my advisor, I was really excited about the research in his group and his vision of kind of the revolutionary role that he saw for fabrics to play as acting as functional systems rather than just passive objects. I began to see how interesting fabrics are, really, because you could consider them one of the most ancient of all technologies, and they're still used universally today. And if we look at fabrics from thousands of years ago, actually the structure of the weave is really similar to the fabrics that we use today. So time has proven that these are really ideal materials for flexibility, large area coverage, and interacting with the human body. So fibers come into that because they're the building blocks of the fabrics. By introducing new capabilities into fibers, we can really create interesting fabrics that are functional in a lot of ways.
Right. One of the very first things anybody learned how to do is like weaving clothes. And now you can we're going to get into some of the more interesting things that people might not know you can do with fabrics as we go.
Yeah.
Along the way, I think we need to set up one term that comes into play for how this works. Piezoelectric effect. What is that?
The piezoelectric effect is a phenomenon where certain materials generate an electric charge in response to mechanical stress. So if you apply pressure to these materials, if you bend them, compress them, they produce electricity. And then the reverse is also true. So you can apply an electric field to these materials and they will change shape or deform or move. So this effect was discovered by physicists in the 1800s. They found that certain crystals like quartz exhibit this property. And so the way that it works is, imagine you have a crystal of a piezoelectric material. And when you apply a pressure to this crystal, it causes a shift in the position of the atoms within the crystal lattice. And this shift kind of disrupts the balance between negative and positive charges. And that gives you a net charge, creating a voltage across the crystal, which is really useful because then we can read that out and have it interact with our electronic devices. Piezoelectric materials are used in sensors and actuators. And then in my research, I've focused on acoustic applications, so using them as microphones and loudspeakers.
Right. I was going to say with the microphones, like sometimes with certain string, like acoustic string instruments, they'll have it in there.
Yeah, exactly. So it's picking up on those vibrations and then converting that into an electrical signal, which we can then read out.
So how do you then put that into a fiber?
In Professor Yoel Finks' research group, we make a bunch of different fiber devices, and we use a technique called thermal drawing to make our fibers. In this technique, we combine multiple materials in a specific architecture to make what we call a preform, which is the scaled up version of the final fiber that we want to create. So to make fibers that are in themselves devices, we have to combine multiple materials to be, the functional material and the electrodes and the cladding, and they have to have a specific structure. So we make this preform that is on the scale of centimeters, and then we place it into a furnace where it heats up. And as it begins to heat up, the materials start to flow and it gets scaled down into fiber. So the materials don't mix together at all when they're flowing, but they kind of all stay in their own lane. And the cross-sectional dimensions of the preform begin to decrease and turn into the dimensions of the fiber, and it gets longer. So it's similar to the way, like if you've ever seen taffy candy being kind of pulled and stretched, it's kind of like the same idea. Using this technique, we have to choose materials that all soften at a common temperature. And so we choose a piezoelectric polymer, which is called polyvinyl diene fluoride trifluoroethylene, or PVDF-TRFE. And we choose other materials that have similar melting or softening points to this one, and we can combine them all together and make this structure fiber.
I was a little curious about what the scale of it, if it was like a lot thicker or if it was more like any piece of clothing fiber.
Yeah, so the final fiber is about 1 millimeter wide, but we can also make it thinner than that. The one that was used in this paper was about 1 millimeter wide.
So thinking about the results of this paper, you have a couple different fibers that are in work, muslin and silk. And I wanted to ask you about the kind of results difference you had.
Yeah, so we create acoustic fiber is what we call it. So it's the piezoelectric material, and then it has a couple other materials that can collect the charge, and then a material that encapsulates it all. So it's all, flexible and waterproof, which is important when you're putting it in clothes that need to be washed. But yeah, then we wanted to understand, how does the actual fabric that this fiber goes into, how does the structure of that fabric affect the performance? So we can have a piece of fabric of just traditional material. So muslin is a cotton fabric, or silk people are familiar with. And then we can have just a single acoustic fiber that we sew onto it, or we can weave it into the fabric, and it really transforms the whole fabric into a microphone or a speaker. And so in this case, we are testing, how does the structure of the muslin or the silk affect the performance of the fabric as a loudspeaker. And these two fabrics, while they're different, when we look at the bulk properties and the vibrations we would expect them to generate, they're actually pretty similar. And so we would expect the performance of the sound energy, the sound output that they generate, to be similar as well. But we find that the silk actually performs a lot better than the muslin. And so where these fabrics are different is really their pore size. So the gap between the yarns that are perpendicular in the weave. So for muslin, the average pore size is about 170 microns, whereas it's like 50 microns for silk. So silk has much smaller pores. And when we think about the fabric working as a loudspeaker, we're applying a voltage to the acoustic fiber, and it starts to vibrate. And this causes the whole fabric itself to vibrate. And as it's vibrating, it's pushing the air to create pressure waves, which is the sound that we hear. And so if we have something that has much larger pores, it's not going to be as effective as pushing the air, because the air is just going to flow through those pores rather than being pushed. We also found that the size of the pores relative to the frequency of sound that you're trying to generate is also important. So even though fabrics are porous materials, they can be effective speakers. We just have to pay attention to how the pore size compares to the frequency of sound that we're generating.
You mentioned that it could be used as a speaker and a microphone, and I think we should loop in people that aren't necessarily into the weeds with audio stuff with how that is possible to do both things at the same time.
Yeah, so as I said before, like with the piezoelectric effect, it works both ways. So you can apply a pressure and generate an electric charge, or you can apply an electric field and cause the piezoelectric material to move. With those in mind, if we think about how a microphone works, so a piezoelectric microphone is going to vibrate in response to sound waves. So sound is a pressure wave in air. And actually, when you hear sound, like our clothes are actually vibrating in response to that sound. So if we have a fiber, an acoustic fiber woven into our clothes, it can pick up on these really small vibrations that can be on the order of nanometers. And the bending that the fiber experiences then produces an electric charge. And that we can read out with our electronics. And that's how it works as a microphone. On the other hand, for the speaker application, if we apply a voltage to the fiber, it will start to vibrate. and whatever surface it's on, so like we, sew it or weave it into a larger fabric, it will cause that whole fabric to vibrate. And as it moves, it pushes the air and creates these acoustic pressure waves, which is the sound that we hear.
Right. Like if you've ever been at a concert and had the speaker, you can feel when the bass starts kicking in.
Yeah, you can even see it sometimes. Yeah.
Was there any challenge kind of getting the fabrics together to do this kind of testing?
So I think there's definitely fabrication challenges in creating the acoustic fiber itself. But then as far as making the whole fabric, we're able to incorporate it in pretty seamlessly with just a normal fabric. And we're really lucky also at MIT in our research group, we have really strong collaboration with the Rhode Island School of Design. So we work with people who really know how to weave and knit and do a lot of interesting things with fabrics. So their expertise is really important in this work as well.
Right. Collaboration from different points of view is always very helpful.
Yeah.
So thinking about the use of it for deadening sound or suppressing sound, can you talk a little bit about the two kind of techniques that you displayed in the paper?
Yeah. So the first one we call direct acoustic suppression in the paper, and then the next one we call vibration mediated suppression. So this direct acoustic suppression is maybe the sound cancellation that people might be familiar with already. So it's like the active noise canceling that we have in earbuds and headphones. And how it works is when you have an unwanted noise, your headphones are actually going to create a sound wave that's kind of the opposite of that unwanted noise. And so those sound waves will destructively interfere with each other and cancel out. And so when it gets to your eardrum, you actually don't hear any of the noise. And so this is a really effective technique, and we've seen it, really explode over the past few years. It's pretty common now to have in headphones. Yeah.
Maybe standard even.
Yeah. But it's limited because it only works in a small volume. You don't see an active noise canceling, module that you can place in your home or something to cancel sound in a room. So it only works in a small volume, close to the ear. But we were able to demonstrate this with the fabric, and we found that we're able to decrease the sound about 20 decibels. So for context, that's like the sound of a normal conversation to a quiet room, just like the noise floor in a quiet room. But yeah, we were looking to see, is there a way that we can cancel sound in a larger volume? And so that's where we came to vibration-mediated suppression. And really, this technique relies on the fact that most of the sound that we hear is transmitted through vibrating solid structures. So for example, if you live in an apartment and your upstairs neighbors are noisy, or your neighbors across the hall are noisy, it's not that the air from their space is entering into your space. It's that the vibrations are passing through your walls. So the sound on their side of the wall is causing vibrations in the wall, and that vibration is causing sound waves in your space on the other side. And so the idea with this vibration-mediated suppression is that if we can stop those vibrations from happening, we can stop the transmitted sound as well. This was something that had been kind of talked about before in literature, but people haven't been able to demonstrate it with both acoustic measurements and also measurements of displacement and vibration. And so with this, we were able to have an unwanted noise and then our acoustic fabric speaker, and we were able to adjust the phase of the vibrations of our fabric and actually cancel out the vibrations up to a 95% reduction. So that was pretty exciting to be able to see, in our measurement setup, we can see the vibrations and then just see them kind of go away.
I don't know if you've done the data, but I'm going to ask this question.
Okay.
Could you tell me, or do you know how that might compare to something like the soundproofing that's in the space I'm in behind me? This is normal, like acoustic foam that you might see in any audio space.
Yeah. So with it depends on the frequency of the sound, but with passive materials that cancel sound, like acoustic foam, that's like a very common thing, we really need a lot of material to get the same level of sound suppression. So with our speaker, we were able to decrease the vibrations 95%, and we also were able to reduce the sound pressure that was transmitted. We measured it to be reduced by 75%. So that's really big. And it's, using a fabric that's 130 microns thick. So it's a very thin silk fabric. If we were trying to do the same thing with acoustic foam, you would need like tens of centimeters for it. So, your room just got a lot smaller if you're lining the walls with all that foam. So that's really one of the key advantages of this.
Thinking about it as a practical application, would it be a room inside a room if you were building it out into a space? Like, would you have to have some sort of space for it to do the vibration behind it? Or could the actual wall, I guess, be like a wallpapered with it or something?
Yeah. So I really think fabrics are already all over our lives, and the most maybe straightforward use would be a curtain that does the sound suppression. So just having a curtain over a window or over a wall that would suppress sound, that's kind of the vision for it.
Could it just hang like that? Like I thought it had to be kind of taught to work.
So actually, like in the paper, we show that the fabric is also effective as a speaker when it's just in a hanging or draped state.
Oh, nice.
We a lot of times mount it into a circular membrane just for...
I think that's what I was catching on.
Yeah, just for like reproducibility and kind of understanding what the system is. It's mathematically, it's like a lot cleaner of a solution to have these controlled boundary conditions. What we show a lot in the paper, but we also show it playing music in a draped state. So I actually had it playing some Bach, and it was you could hear it, and it doesn't have to be pulled tight or anything.
Okay, what was the biggest surprise for you in developing this fiber?
It was very exciting to try these noise cancellation techniques. And I think the first time actually seeing, we measure the sound pressure level, and the first time that you actually see it drop and get lower and lower, it's like, oh my gosh, we're actually canceling sound. But I think the biggest surprise was really with the vibration mediated suppression. We're kind of wondering, where does that incoming acoustic energy go? Because it's not being transmitted through the fabric. Like, is it being absorbed? And we actually found that the fabric is reflecting the sound pressure. So that acoustic energy is being reflected. So we don't usually think about fabrics as reflective materials. We might think they're actually good materials to absorb sound. But by controlling the acoustic fiber and controlling the vibrations of the fabric, we can actually modulate the reflectivity of the fabric and make it a reflective material. So the sound, the unwanted noise, that incoming sound, it actually just kind of bounces off of the fabric, and we measure a higher sound pressure level on the other side of the fabric.
While we have you, I know there's a couple other areas that this has been explored with, and I wanted to hear about some of the other acoustic fabrics that you've been working on in the lab.
Yeah, so we talked a lot about the fabric as a speaker, but it also works as a microphone. It's very sensitive, picking up vibrations on the order of nanometers, and we've used it in applications like listening to heart rate. The fabric just sewn onto a shirt can pick up the heartbeat, which is really exciting for different healthcare applications. And I've also done work with using multiple fibers to detect the direction of sound, which is also really useful. We found that, 2 fibers on a shirt can actually estimate the angle of a sound source within 1 degree of accuracy. So that's better than the human ear actually at detecting the direction of sound. Other students in the group and my advisor have really pioneered different fibers that can work as batteries, or fibers that have LEDs in them or sensors. And actually, we can do some computing on the fiber level. So there's so many possibilities. And I think fabrics are really just universally used. And there's a lot of things that we can take advantage of with incorporating more functionality into them.
Right. Having your clothes do a lot more than just kind of protect you from the elements.
Yeah, exactly.
I also want to ask you about your graduate research fellowship experience. What did that mean to your development, and how does an award like that impact the way you feel about yourself, the way you go about your next couple of years.
Yeah. I'm very grateful that I was supported by the NSF Graduate Research Fellowship during my PhD. It definitely gave me the ability to pursue my research and my interests without worrying too much about finding funding or anything. And I think the really unique thing about this fellowship that was so great about it is that it funds the researcher rather than the specific research. Because when I was applying to it, I think during my first year of grad school, I really didn't know what was coming up, what the future of research would look like for me. And I don't think I would have imagined that I would be working on fabrics as microphones and loudspeakers. It sounds pretty out there, and it wasn't something that was even on my radar. So I'm really grateful that I had the support of NSF and I was able to, really follow my interest and curiosity in this direction.
So last question for you before I let you go. What is next? What's the next steps in your research? What are you up to?
Yeah. So in the fibers group, we're hoping to continue to expand the applications of the acoustic fiber and also work with the fabric loudspeaker to kind of create more complex algorithms to do sound suppression. And for the acoustic fiber as a microphone, we're really interested in healthcare applications. So doing heart monitoring or lungs monitoring. There's a lot of noises that come from the body that kind of just go unnoticed and uncaptured. And we think there's a lot of potential for what the acoustic fabric can do.
Special thanks to Grace Yang. For the Discovery Files, I'm Nate Potker. You can watch video versions of these conversations on our YouTube channel by searching @NSF Science. Please subscribe wherever you get podcasts. And if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.